12.6, proving triangle congruence by angle, side, angle, and angle, angle, side. So these will be our last two ways to prove that triangles are congruent. Let's start with angle, side, angle. So if two angles and the included side of two triangles are congruent, then the triangles are congruent. So specifically here, if we look at triangle ABC and DEF, do you notice that we have the two angles that are congruent? Now on this one, the included side, once again, has to be the side in between the angles. If it's not in between, then this theorem will not work. But if that's true, then we can say that triangle ABC is congruent to triangle DEF. Then we have angle, angle side, which says if two angles and the non-included side of two triangles are congruent, then the triangles are congruent. So in this one, we still have these two angles. But notice now the side is not included. Okay, it could be this side. It could actually be the side over here as well. That one is not included. But it cannot be AC or DF. It has to be the outside one. So angle, angle side. Then we can say that triangle ABC is congruent to triangle DEF. Example 1. Identifying congruent triangles. Can the triangles be proven congruent with the information given in the diagram? If so, state the theorem you would use. So, in example A, we're given a whole bunch of angles, and we're also given parallel lines. So in this one, if I'm looking at my parallel lines, let's look at these first. Parallel lines cut by a transversal. I can say that angle 2 is congruent to angle 4, and the reason is because they are alternate interior. I can also say that this line that kind of cuts through the middle here, WY, so I can say that WY is congruent to WY because of the reflexive property. Then, what if we go consider the other set of parallel lines? So if we consider this guy's parallel and this guy's parallel and cut by that same transversal, then we have angle 1 is congruent to angle 3. And the reason here is also alternate interior because we have parallel lines. So now it looks to me that we've got an angle, the side in between, and then another angle. So here we could say yes, and the theorem would be angle, side, angle. Okay, letter B. Can we conclude? So letter B I'm looking at, and it looks like if we look at this out one, or outside triangle, do you notice that this guy's congruent to this guy? Which means ultimately this is an isosceles triangle, so I know that the base angles are congruent, which gives me an angle and a side. Well, then I'm going to look right here, and I know that this is congruent to itself. So this would be, let's see, side, side angle. I have two sides in an angle, which would be like side, side angle, but that's not a theorem. So that won't work. I don't know anything about those angles, so we can't say those are congruent. I don't know anything about those angles, so I don't know if those are congruent. Some people would look at that and say it looks like it's cut in half, but there's no way of knowing that. So here there's not enough information. We cannot conclude that those are congruent. Letter C. Okay, letter C, we already know that DG is congruent to GF, so that's good. And then we have a right angle which is congruent, so we have an angle. Then I can conclude that this angle is congruent to this one. So I could say angle EGF is congruent to angle HGD. And the reason is because they're vertical, which gives me an angle, and a side. An angle, and a side. And that is a theorem. So here we can say yes by the angle side theorem. Letter D. So letter D, they're giving us angle M, and they're giving us angle P's. So we already have two angles that are congruent. Then I'm going to look at this and say, okay, well, what about MP? That's side. Do you notice they both share MP? So MP is congruent to MP by the reflexive, which gives me an angle, a side, and an angle. That is a theorem. So here we can say yes by the angle side angle theorem.